Okay, it's a great pleasure to introduce Dr. Omer Bobrowski, currently from Technion, Israel Institute of Technology, who will talk about persistent cycle registration and bootstrap. Over to you, Omer, please.
Thank you. Thank you for the invitation. I'm happy to be part of this conference. I should mention that this is part of the master thesis of my student Yohai Reani, and much of the work I'm going to show you is his work, and also many of the figures and the drawings that you see I borrowed from him, so he deserves the credit. I want to start with an overview to the problem I'll be discussing, and try to give you a motivation to what we're trying to do here. And the motivation will start with two persistent diagrams. Suppose I'm giving you one on the left, one on the right, and I'm asking a simple question. When you look at these diagrams, can you tell me, are there any significant or any meaningful feature, any meaningful cycle that you see in those diagrams? Are there, and if so, can you spot them? Can you tell me which points is an interesting feature that I should care about? And traditionally, what you do is you consider the distance from the diagonal, or the length, or some other measure of the death and birth. And probably you look at the diagram on the left and you say, okay, there's a point that's quite outstanding, it's far from the diagonal, probably represents some meaningful features. Everything else is kind of a noisy thing. And on the right, it's quite hard to say. I mean, there are some points a bit far from the diagonal, but mostly concentrated next to it, and it's probably mostly noise. And now I'll show you where these diagrams were generated from. And these are 2-point clouds. So I'm taking check filtration. And what you see on the left is that the data here, the points here there's a big cluster on the left with something like 1,000 points, very dense, and also organized around this ring, and also 4 outliers. And the cycle that you see here that you might have said that is interesting and significant, just the random outliers far away from the center generated, and you cannot spot the interesting cycle, though just intuitively should be interesting because it's a dense region with a hole inside. It's hard to say that it exists here. And on the right, where you can barely see any interesting cycle, actually, when you look at the data, you see that there's a lot of noise, but in this noise, there is a hidden, there are a few clusters, very dense also, and they're organized also in some ring kind of structure, and they should form some cycle, but this cycle is hidden in the diagram. It's very hard to spot it. And the bottom line from this example is that in many cases, measuring persistence, measuring death versus birth by looking at the diagram is not the best way to find so-called statistically significant things or anything that is meaningful or interesting. It could be misleading just by looking at the numerical death and birth value. And what we want to propose here is an idea for other kind of measures you can apply to persistent diagrams. And for the time being, we call it something like prevalence. And the idea is the following. Suppose that I have this data set here, similar to the one I had before. There is a dense ring over here and some outliers. And when I look at the cycles, there's going to be gamma 1 here, that's one cycle, and another one cycle. And ideally, I would like to say if one of them is significant and interesting or not. If I look at the barcode and I measure persistence, then gamma 2 is going to be a longer bar than gamma 1. So if I just blindly do it, I'm going to say that gamma 1 is more meaningful than gamma 2 is more meaningful than gamma 1. And that probably is a wrong answer because statistically there's much more information here. And we want to have something that captures this notion. What we want to aim for is a different measure, which we'll call it for now P gamma, where for every cycle gamma, we want to be able to tell you, okay, if I have access to the distribution generating the data, and I'll generate a new sample from the same distribution, how likely it is that I'm going to see the same cycle appearing again. Okay, and if there is a cycle that is very in a very dense region, and it's going to appear in many, many samples because I have enough points and the density is very high, well, the outliers will be hard to recover. In many samples, I'm not going to see that. And so if I have a way to access this measure, which I call prevalence, and compute those probabilities, then I would find out that this cycle has a much higher probability than the other one, and that, at least in my view, better capture which of them is more significant than the other. And so this is the motivation for this work, and we were trying to aim to get a hold or to get our hands on something like this prevalence measure for cycles. The main question is how do we calculate something like that? I mean, even if you, I mean, the problem is to begin with ill-posed, but even if you had access to the distribution generating the data, even if you have access to the distribution, it's not a probabilistic question that you can easily form. It's a pretty, even phrasing the question probably is difficult, let alone computing this thing. And what we want to propose as part of this framework is to use the idea of statistical bootstrap to do that. Bootstrap is a whole area in statistics, pretty old by now, first presented by Bradley Efron. I'll just tell you the gist of it, just the main idea. And that is that when you do statistical estimation, for example, it's not enough for you to have the quantity you want to estimate. You also have to, you want to have some kind of a accuracy measure to say how, to have a confidence interval to say how reliable your estimates are. So suppose that you have data you sample from some source and you compute an estimate of it. Let's say you take the average or something like that, and you want to say how reliable this estimator is. Now, if you know what the original distribution is, or if you have some central limit theorem, something like that, then the classical statistical method that will give you confidence intervals or variance estimates and so on. But in many cases, it's either inaccessible or very difficult to compute. And then the bootstrap idea tells you that instead of going back to the original distribution, you should think of your sample as a good approximation to the original distribution and just generate new, what it's called subsample from this original data. So what you'll do is you'll pick random points from the left and generate new, usually smaller, but doesn't have to be, new samples where you just pick points from the original sample. Those are called subsamples. And then what you do is for each of those subsamples, you can compute the value of the estimator that you're interested in. And now you don't have a single value, you have an ensemble of value, and you can use this ensemble to get some kind of an approximate distribution. Okay, so now instead of just saying this is the estimator, you also say, you can say how approximately how this estimator is distributed, and maybe you can say something about the variance, maybe you can derive confidence intervals and so on. And this is without using anything from the original distribution, you just use the data itself. And this is the main idea of statistical bootstrap. And we wanted to use this concept and apply it to the problem that I showed you before. So, before I go back to the problem before, I should mention that there is the idea of putting bootstrap in the pipeline of TDA and persistent homologies has been done before, and the fundamental work is by Faizi et al. From 2014. I just want to quickly tell you what the idea there was. So in this work, they assume that there's data sampled from a manifold. You want to recover the persistent diagram of the distance function from the manifold. And in order to do that, and all you have is just random samples, what you do is you subsample your points. So you generate many random samples from the original point cloud. And then what they do is they use the stability theorem to derive what they call confidence sets. Namely, you look at the persistent diagram that you have from your random point, and you can say how close the original diagram of the manifold is. And so if you have a point and you draw a square around it, you can say that, okay, within this square, there should be a feature in the original manifold. And this also allows them, at the end of the day, to derive this band that you see here, such that they say, okay, if points are within this band away from the diagonal, then we will consider it as noise because it's not an original feature in the manifold, but everything else will be considered the signal as something that comes from the manifold. And this is a really nice idea, and I think that's the best work in this direction that I'm aware of today. Two key differences between what they're doing and what we're aiming to do is that they take the entire persistent diagram as a whole object, and the whole confidence sets and all the estimates are done for the diagram. Whereas we want to pick a specific cycle that we might consider as interesting and then say something about this specific cycle. And also, at the end of the day, their way to measure what is a significant or not significant cycle still rely on how far away you are from the diagonal, which I showed you at the beginning, in some cases could not be the best thing to do. So this is some history. What we want to do now is to connect these prevalence measures that I introduced to you before and show you how to, maybe we can do it with the bootstrap idea. So I remind you, we have a sample of points. Here we have 2 cycles. For each of them, we want to estimate or to get a hold on this value, how likely it is that we're going to see a similar cycle if we have a new sample from the same distribution. What we're going to do is we're going to use the idea of subsampling. So we're going to take the same point cloud and just sample from it several times. Okay. Sometimes we're going to see this gamma 1 appearing. Sometimes we're going to see gamma 2 appearing. And the point is that since there are many points that creates gamma 1, we're going to see it many times. And since there are very few points generating gamma 2, often it's going to not be existing in our sample cycle. And then what we're going to do is just empirically compute this ratio. How many times do we see gamma versus how many subsamples we have? And that gives us an estimate to this quantity, which we call P gamma, how likely it is to see a cycle. And at the end of the day, we want to say that if this score, this value is very high, it means that this cycle is very significant. It's going to appear over and over again in many samples, whereas something with a small value is probably just an outlier. And this leads me to the main topic that I want to discuss and the key challenge in this framework that I just outlined to you. We have one point cloud here and many other point clouds as subsamples. And what we need to do is we need to have a way to say, okay, we see a cycle here, gamma 1, and then we're looking at a different point cloud and we want to say, okay, there's a cycle here and those 2 cycles are the same thing. Okay, but we're looking at 2 different diagrams, 2 different spaces, and we need to have a way to say, okay, a cycle here is the same as the cycle there. Otherwise, this whole framework will not work. And this is the main challenge. And what I'm going to show you next, and what we call cycle registration, is sort of a generic way that we try to address this problem, moving away for a while from this bootstrap. So the bootstrap, you can think of it as an example, as a motivating example. But now I want to address this problem in a more generic way. So loosely speaking, what we want to do in cycle registration, what we call cycle registration, is the following problem. Let's say we have 2 spaces or 2 filtrations later, and we have features, we have cycles, and we want to say about 2 cycles whether they represent or they're coming from the same underlying phenomenon. So you can think, for example, about if you have 2 recordings from different sensors and they record the same thing. Okay. What's happened? Oh. Okay, so let's think, for example, on homology. So let's say we have X and we have Y. Each of them is a measurement from different sensors. And we want to say that maybe this cycle over here represents the same phenomenon as the cycle on the right. How do we do that? How do we take 2 spaces and say this cycle matches the other one? And probably more difficult to do would be to look at precision diagrams, to look at those points in the diagram and say, okay, this point over here represents the same feature as the one on the left. And that's what we call cycle registration, and that's the problem we're trying to propose a solution for. It's not there's not a unique way to do it. And that's what I'm going to show you next. So we start with, before proceeding with homology, just do it with homology. So the assumptions is the following. We say that we have 2 spaces, X and Y, and we want to compare them. We want to match cycles in X with cycles in Y. The key ingredient here is to say that we have a 3rd space, Z, and mappings going from X and Y to Z. Because otherwise the problem is completely ill-posed. How do we compare 2 things that are completely unrelated? So Z would be the thing they have in common. In all the pictures that I'm going to show you, F and G will be the inclusion map, but it really doesn't have to be. It's just for the visualization purposes. Okay, so assuming that we can map X and map Y into a common space Z. And so we think of Z as a common frame of reference where we can map all the cycles into, and then we can find those matchings. And this frame of reference will highly depend on the problem that you're trying to solve and maybe the different kinds of solutions that you're trying to achieve. So it's a sort of one of the ingredients that you have to properly choose and carefully choose. But we assume that you have that. So you have these mappings, and you also have the mappings in homology. And now if you want to say whether two cycles in X and Y match, what you do, so for example, we have gamma on the left, the red thing, it's matched to this cycle here, and delta on the right is mapped to the other one, and we see that in Z, they are homologous cycles. So this will be our conditions. If we have two cycles in X and Y and they are mapped to homologous cycles in Z, then we're going to say that those cycles are matched, they are equivalent. Of course, this equivalence depends on Z. So for different Z, for different spaces Z, different cycles might match. So this is the fundamental idea of what we're trying to do. Just look at the mappings and look at things that are homologous in this mapping. And this is where it ends more or less for homology. But what's more complicated to do is to generalize this framework to persistent homology. Okay, so next what we want to do is to look at persistent cycles. And one of the challenges here is that when you look at persistent diagram and you're trying to match things, maybe things that you will consider as a match, they live in different intervals. They have different death and birth times, and therefore not necessarily easy to find a point where they both live and they're both homologous, and it's not going to be for the entire lifetime. So we're trying to work around that. The key ingredient we use here is called the persistent image. It's coming from an old paper by Cohensteiner, Edel, Spooner, Herr, and Morozov. And the idea is the following. Let's say you have two filtrations, X and Z. So that will be X at the top and Z at the bottom. And as before, we have mappings, but now between every X to every Z. So this will be the functions F. So you have a sequence of functions as well. And we're assuming that the functions commute with the inclusion. So this diagram is sort of commutative. And so we have this commutative diagram in homology, and basically this allows you to define what they call the persistent image, which is just the persistent homology. When you look, instead of either the filtration of X or Z, you look at the filtration, not the filtration, you look at the sequence of images of these mappings. And what it gives you sort of a way to look at cycles that exist in X, but from a point of view of how they look in Z. And what I mean by that is that if you think of the persistent homology here, so there is a cycle that is born in time 2, and it will die at time 4, so the barcode will look like that. It's an interval of length 2. But now when you think of this cycle from the perspective of how it looks like in Z, then over Z it dies earlier because something in Z kills it before. And therefore, when you draw the barcode for this persistent image, it's going to be a shorter bar. Okay, so we want cycles in X, but how they look like when we project them into Z. And we want to use this idea in our cycle registration framework. Okay, so what I want to show you now is the main idea of how to match cycles in persistent homology. As I said before, it's not a unique solution. It's just what we propose to do, and seems to be working really nicely in many cases. And the idea is the following. We have the same picture as before. We have now, instead of X being a space, think of X as being the filtration. So maybe you're looking at the distance function from this space, or this is just the best way we can think of visualizing this. Okay, so we have a filtration on the left, you have a filtration on the right, and you have again a filtration in common. That would be Z. And F here is also a sequence of functions inside the filtration. Now, the first thing you can do is you can take X and find the persistent diagram representing it. And there are two cycles here, and you're going to see 2 points in the diagram. The blue one I'm going to call gamma. The gray one I'm not going to name. The second thing we can do is, instead of looking at X, looking at the persistent image going from X to Z. Now, what will happen here is that we're going to have something that corresponds to the blue cycle, because it's not trivial also in Z, but the gray one doesn't appear here because in Z it's a trivial cycle. So when we do this mapping, we no longer see it in the diagram. So we're down from 2 points to 1. But the point is that since we're looking at cycles that are created in X, and we're looking at the image in X, those two cycles, gamma and gamma tilde, they should have the same birth time because they are generated by faces or by chains that are existing in X. And we can do the same thing on the right. Here we have two cycles. Both of them are mapped to something non-trivial in Z. And again, since everything is generated in Y, they must have the same birth time. So we have a way to just look at the diagrams. We have 4 diagrams we have to compute, and we have ways to say, okay, what matches vertically? And now we want to match things horizontally. We want to say something in Y matches something in X. And for that, we'll have the following observation. Things die in this image persistent when something in Z kills them. So if at some point those two cycles, the purple and the blue, if at some point they're homologous, they're going to be killed by the same chain in Z. Instead, they're going to be killed by the same chain, they're going to have the same death time. Okay, so now we're looking at the persistent images on the left and on the right, and we need to find cycles that have the same death time, and then we're going to declare those two cycles, gamma and delta, as equivalent or as a matching. Okay. And in fact, the way we do it is sort of in a reverse order. We compute those two persistent images. We're going to look for cycles with the same death time that will tell us that there is some matching between X and Y. And then we're going to go back upwards and see what the original cycle was by matching the birth time. Okay, but this way we again we need to have this middleman, this Z, which is the common frame of reference, and then we have to calculate those 4 persistent diagrams and just use matching between death and birth time. One assumption that is hidden here is that there are no 2 cycles with the same death or birth time. Otherwise, things might fail or might behave in a non-intuitive way. There's a question.
Sorry, you sort of just answered my question. I was going to ask what happens if there are multiple cycles with the same death time.
Yeah. So things will not work as you want them. Probably it will be non-intuitive, but at least what guides us is that in any setting where your data is random, it will happen with probability 0. If you just have something that's sampled from some distribution, it's unlikely that you have 2 cycles with exactly the same birth time or death time. So that's sort of what guides us. But you're right that in principle, in the more general framework, if there is this this case that you have 2 cycles with similar death time, then you have to be more careful or maybe improve this or think about how to handle it.
So computationally, our persistence parameter isn't usually a real number. We have some discrete set.
Sure.
And so there is going to be some finite probability of having the same death time.
Well, it depends. Again, we're thinking of, again, a motivating example is looking at point clouds, and then you're building a check or if complex, so you don't discretize, you just use the distances between the points. And then it will be more accurate. Yeah.
A good point.
But again, in some cases, it might not be, it might require improvement or more considered. Okay, so this is the main ingredient. This is what we call cycle registration. And again, I showed you very briefly how we think about it and the solution that we propose. And it's not much more expensive than computing persistent diagrams, just that we have to compute a few more and do this comparison. Now I want to go back and discuss the application, the motivating application of this bootstrap for geometric complexes. Before I'll show you how it works, just a quick reminder, I assume most people here know about this thing, but we'll mainly think about the check and the RIPS complex. So you have a finite set of points, think within Euclidean or other metric spaces. So in the check complex, you draw balls of radius r, and you look for, if you have k plus 1 point intersecting, you place a k-dimensional simplex. So you get this picture on the right. Those 3 balls, for example, do not have a common intersection, so the triangle here is empty. The V-torus RIPS is similar, just that you look for pairwise intersections. So you have more simplexes than in the check. For example, this simplex, it's enough because we have all the pairwise intersections, so you place a triangle. So we mainly think about the check and the RIPS, but in principle, you can think about any geometric complex you want, as long as it will satisfy what I'm going to show you in the next slide. So first of all, before the bootstrap, just how do you do cycle registration in geometric complexes? And I think it's a very natural way. So we're assuming that we have 2 point clouds. We want to compare cycles between those point clouds. And the common frame of reference would be just the union of the points, assuming they're sort of lying in the same space and so on. And then what we do, we take the check or RIPS complex, or again, any other complex. Well, again, we have in mind this diagram that I had you before. So sorry, the X and Y, the Y and Z here should be switched. Z should be in the middle, and we should have Y. So we either take the check or the RIPS, and the matchings would be just the inclusion map. And the property that we use here is that the fact that if we have inclusion between the point sets, then we also have inclusion between the check complexes or the RIPS complexes. This, for example, doesn't work with the alpha complex, because if you add more points to a point cloud, the alpha complex doesn't have to satisfy this inclusion. So the alpha complex doesn't work. In fact, we have some another paper with a solution for that, but that's a different story. So use this framework and just again an example to have in mind. So let's say that you have point sets on the left. We compute the check complex. We find this red cycle. On the right, we have another set. We find the blue cycle. Now we put the point sets together and we have a much bigger complex. And what we see is that the blue and the red cycle in the new check complex, they are homologous. They surround the same 2 holes. And so we can go back and say, okay, we have 2 different point clouds, but this red cycle is a match to the blue cycle on the right. And that's sort of the idea that we're using here for point clouds. Okay, so now that we have this way to take 2 point clouds and say, okay, which cycle are matching between the 2 point clouds, we can go back to the prevalence and the bootstrap problem that I showed you before and try to propose a solution. So I remind you again, the main idea of what we're doing is we have an original sample. We generate many sub-samples from it. So I'll tell you in a second how we sub-sample, but we have random samples from the original set X. We use either the check or RIPS complex. And what we want to do, we want to take each of the sub-sample, compare it to the original set X, and find matching in order to count how many times the cycle repeats. Okay, so we're going to compare X1 to X, and then we're going to compare X2 to X, and so on. So we're going to have this cycle registration framework going on and on and on for each of the sub-samples. And then at the end of the day, we can compute this bootstrap version of the prevalence value, and we just go over all those matchings and find how many times you could match gamma 1 or gamma 2 with the subsample and just divide it by the number of subsamples, and then you get this prevalence value that you want. So that's the main idea, or the basic idea of how we want to address this cycle prevalence measurement. What I'm going to show you in the next slide is that it's not working as we would like it to. Sorry, before that, just a quick word on how we subsample it, but maybe it's not straightforward. So we have the original sample X consisting of n points, and we have a subsample which are supposed to be points sampled from X, could be different number of points, bigger, smaller, depends on how you want to do things. The question is, how do we do that? So you have the original set X, let's say that this is there's 5 points. And then usually in Bootstrap, what you do is you just sample from X with replacement. So you can choose several points several times. And so for example, if we do that, maybe we got this point in the corner once, this point was sampled 3 times, and this point in the corner was not sampled at all. So we get some random subsample. This is what is usually done in Bootstrap, but this is not very good here because it means that you're going to build a simplicial complex with multiple vertices at the same point. It's A, not very useful, and B, might be leading to some confusing results. So just to solve that, what we're doing is just adding some perturbation to the points, some Gaussian noise, and then they're moved around a little bit. So you get this picture on the right. So it's still some kind of subsampling, but with a little bit of perturbation. Alternatively, one can think of that as, this is just sampling from the kernel density estimate, where you take the points, you compute the kernel density estimate for the Gaussian kernel, and you just sample from this distribution, which we call the F hat, the same result. So this is our subsampling. And as I said before, the first thing I want to show is that this thing doesn't work as great as we hoped it would. And the main problem we observed is that when you just have noise, when you have sample with no cycles in it, you're going to have a lot of prevalent cycles. So for example, here we took 1,000 points in the unit square. And for example, this red cycle was found. And we did this whole subsampling thing. So we generated many subsamples. And it turns out that the way we do it, in many of the subsamples, we find this blue cycle that is a match to the red one. And we can collect it for all the cycles that we see, and you see a very bad picture. And what you see here is this prevalence value that we computed for each of the cycles in the noisy sample. So most of the cycles that we see are very prevalent. And that's not a very good result because this is a noisy thing. You don't expect anything meaningful or interesting to show up. So that took us to a little bit of more heuristic refinement. So this measurement by itself, or at least the way we do it, is not the best way to go. So what we did is to refine a way of defining a prevalence. So we're gonna redefine it and add some more information. And what we, or more accurately, Yohai, my student, chose to do is the following thing. We're gonna measure overlap between intervals. So what do we mean by that? Suppose that we have two intervals in persistent diagrams. We can take the union and the intersection, and then we define this overlap coefficient would be the fraction of between the intersection and the union. How much overlap do they have in common? And now for each matching between the original sample and the subsample, we're not only going to count 0 or 1, whether it is 0 or not, but also how much overlap there is. Because the more overlap, it means that the more in common those two cycles share, so to speak. But this is heuristic. There's nothing extremely mathematical here. So I remind you, when we compare the subsample, we have X, the original on the left, Xi is the subsample from the right, and we're looking at the union. And so a new prevalence score will go over all the subsamples. And every time we find a match, we're going to take the overlap between those match cycles in the center, and also the matching between the two spaces on the right and the center. How much delta is matched with delta tilde and how much gamma is matched with delta tilde. So we want things to have as much overlap as possible. And now it gives us a number which is more refined, a score which is more refined. And we'll go back to the noisy problem and noisy example and show you what happened. So now we basically do the same thing. And this considerably took the scores down. So before we had all the scores very close to 100, maybe it's in percent, it's supposed to be between 0 and 1. And it's still not amazing because ultimately you want noisy stuff to be close to 0. It's still relatively high, but it's much lower than before. And one thing that is promising is that it doesn't significantly or at all increase with the number of points. So if you have more and more points and more cycles, the prevalence score is sort of bounded. But probably there is a way to make this better, but at least it works fine for noise. And more importantly, in the next examples, you see that it works well with signal when there are real cycles. So the next example we took is to a two-dimensional torus with 1,000 points. So this is the sample, this is the diagram. Here there are enough points so that the persistent diagram itself is very informative. You see the 2-1 cycles that you expect to see in a torus. And then this is our scores. So you see, we take all the cycles that we see in the persistent diagram. For each of them, we assign this prevalence score. And you see that there are 2 cycles that have a very high prevalence score, and the others are much lower, and they stand out. And again, this is a more statistical thing where it's just a numerics of death versus birth, which might or might not be meaningful. And when we sort of go back to the points and you draw those 2 cycles, these are more or less what you expect to see. There's one cycle that sort of goes on the top and another one that wraps around the side. Another thing that we did is this is from the subsamples. Since we know how the data is distributed, we can just go back and generate new samples, entirely new samples from the same torus. That gives us much improved and much more accurate estimates, just because convergence happens much faster. And here you see it's much clearly that there are 2 cycles. It will be more obvious in the next example. So, but that's in the very rare cases where you can actually generate new points from the same distribution, and you don't have to use the bootstrap. This is the same example, just with much fewer points, 100 points. So this is the sample. Here you only see 1 cycle. Here there is one very prevalent cycle, but it's not exceptionally beyond the others. So it's it's not as sharp as before, but still when we draw the first two cycles in the prevalence score, they are the cycles that you want to see. So the matching does work well. Maybe the prevalence score has to be refined. And if you generate samples from the original distribution, you get much better score than either this one or this one. So here you clearly see that there are two cycles where you could not say that from just looking at the persistent diagram. Okay, but the picture here requires that you can generate new samples from the torus, which in many cases you can. Okay, this is the last example, which I also showed in the introduction. So here we have 5 clusters arranged around the ring. If you look at the persistent diagram, you will not see anything. And if you run the scores, you see that there is one very prevalent cycle coming from the fact that you sample a lot from those clusters. You very rarely sample from the points, and this cycle will show up, even though you cannot spot it at all in the diagram. When you increase the ratio between signal and noise, much more noisy points here, then it's much harder, but still there is something that doesn't exceptionally stand out, but there is one cycle at least with a relatively high score, and you can think of whether or not to use it. I mean, one key problem or one future direction to use how to threshold those values, or how to treat them, and how to decide whether something is meaningful enough. But at least we see that there are cases where persistent diagram will not tell you at all that there's anything interesting, and this will tell you that here clearly there is something here, maybe there is something, and so that's useful. I think I have 5 minutes. Am I right? Started late.
Yeah.
Okay. So I want to show you just a couple of ideas to how to use the cycle registration framework beyond the bootstrap that I showed you. Not in any details, just and we didn't develop them so much, but I think they're nice ideas. First one is to compute distances between persistent diagrams. So we all know the Wasserstein distance. Basically, you take 2 diagrams, you find an optimal matching, optimal pairing between the point based on how far away they are, and then you get some number. And here is an example where this strategy might fail. So suppose that you have a space X, space Y, and space Z, and the blue point here is the origin, so they're all aligned. Those two things will be considered similar. This is just 2 rings, one inside the other, whereas the third one is quite different. The 2 rings are one side by side. Now, think about the distance function from the set and take the barcode. And then this is the barcode that you get here. So the 2 cycles more than 0, and dies at 3 and 5. And here that also 2 bars, one dies at 2, one dies at 4. So if you take the Wasserstein distance with p equals to 1, you get the distance is 2. However, if you go to the right, this barcode is exactly the same as the one on the left, in the middle. And so if you take the Wasserstein distance, you will get a distance of 0. And this is a bit counterintuitive, or maybe not very desired, but you have 2 spaces which are quite similar, but they get a relatively high distance, whereas you have 2 spaces which are quite different, and they get a 0 distance. And the reason for this discrepancy is coming from the fact that when we take the Wasserstein distance, we completely rely on the numerical value of the death and birth value, and we completely ignore where these values came from, and what is the structure that generated them, and whether it makes sense to match points in the diagram. And what we want to propose is to use the cycle registration framework to make a better way to match the points in order to compute a different distance. And the idea is the following. So again, in the Wasserstein distance, we just go over all the possible matchings and take the one with the minimum energy that you need to move one diagram to the other. But now we have more information. If we use the cycle registration, we don't need to search for all pairings. We have pairings. We can take the 2 diagrams, and we can find all the cycles that represent the same phenomenon, whatever that means. We can pair them by how meaningful, or by meaning that 2 cycles mean the same thing. And so we're only going to count those cycles that have a matching. And then, for example, if we take the same diagrams, but our algorithm show that, let's say, this blue and red cycle represent the same phenomenon as these 2, then we're going to match them like that, even though the distance is much bigger. But that will make more sense because they represent the same phenomenon, at least according to our definition. And that can give you a new way to compute distances between diagrams, and that in some cases might be more reliable. And if we go back to the example that I showed you before, so what we can do here, we can try to do the matching. So the matching here, I would put just take the union of the spaces. And now I will look at the barcode. So if I do the cycle registration, obviously the big red and the big blue, sorry, big green and blue will be a match. So I can match these two bars. And also the small green and small blue will be a match. So I can match those two bars. And then I get similar distance to before. The transfer that I need to make is exactly 2. However, if I try to compare these two, then these two bars will still be a match. So the small cycle here is matched with the small cycle in Y. But now these two cycles, the big cycle on the right and the big cycle on the left, do not match. They are mapped to completely 2 different things. And therefore, we cannot pair those points in the diagram or those 2 bars. We cannot pair them. And therefore, we'll have to match them to the diagonal. And that will result in a much larger distance. So now the distance will be 8. And that's much more reasonable result to get for this example. Right? We get that 2 different spaces get higher distance. Remind you, before we had the normal losses and distance that just gave you a distance 0. So this is just an anecdote, or maybe it's something that we would like to pursue in the future. But it looks like it could be a powerful thing to do in some cases. I'll skip that because I'm running out of time. I just want to summarize. So I told you about this idea of cycle registration. Basically, you take 2 spaces or 2 filtrations and you try to say which cycles match between those 2. The main assumption is that you have something in common, some space in the middle. We use the idea of image persistent homology and just compare the death and birth time in order to do this matching. And I discussed you the main application, which is the bootstrap idea. I also showed you this, what I call the guided y-and distance. And there are other ideas that we've been running around. With respect to the homological bootstrap, the main idea is the following. You have a point cloud. You generate many noisy subsamples from the same point cloud. Now you find matching from the original sample to the subsamples. And then you just compute this prevalence score to say how prevalent the cycle is, how often does it appear in the subsample, and how much overlap there is in all the appearances. And that gives you a score that, at least in the toy examples, show to be able to recover things that persistent, just looking at the persistent homology, you cannot recover. And that in some cases where you do have something which should be considered statistically significant, but it's either hidden inside some noise or it's too small to be observed, you can find it with those prevalence scores. And for future, this is just a fundamental idea that we started looking at. The whole bootstrap framework required much more observation. You would like to show that things converge properly. The cycle prevalence score right now is a very heuristic thing. We should be explored much further. The idea of the guided y-and distance, I think it's pretty cool. And the question is how to properly do that, and what examples to show that it's really useful in some examples. And also ultimately look for more applications for this cycle registration to show that it's really can be useful in other areas. Yeah, so the first paper is what I was telling you about. The second one is an improved sort of alpha complex that can be used with this cycle registration framework. And also you can find code for everything I told you about if you want to try to play with it in GitHub. But that's all. Thank you.
Thank you, Omer. Let's thank Omer. Do we have any questions for Omer? John.
Thanks, John Harvey here in Swansea. That's a brilliant idea, Omer. I was just wondering, have you looked at how does the prevalence change as the size of your subsample changes? This is just perhaps a bad intuition, but it seems to me that maybe the noisy cycles would dissipate faster as you took smaller subsamples, whereas the structural ones you might expect to hang around better. I don't know why I have. Yeah.
That's a very good question. I mean, again, the simulation that you saw was run by my students, and he did try to play with a lot of, there are various hyperparameters, the size of the sample, the size of the Gaussian node that you add, and so on. our goal here was mainly to show this idea and to show a toy example that highlights when it could be beneficial, okay, rather than to have a thorough investigating on these specific examples. But it's a very good question. I mean, I don't know if he's here, he might be able to tell you more. I don't know if he showed up, but I don't have a clear intuition of how it will scale with the side of subsamplers. But it's something that's really worth investigating. Again, as a next step to really make this thing more useful. Yeah.
Okay, thank you. And I was also wondering, I mean, did you just go for sampling? That's the standard bootstrap technique. It seemed like computationally it might make more sense to just look at each point and say, with a fixed probability, I include this point. And then your subsamples of variable size, but you don't need to worry about Gaussian noise or little clusters of duplicate points and so on.
You mean sampling without replacement?
Yeah, but the most efficient way, I guess, is to have, to not be too clear on how many points you're going to sample, right? Just each point goes in with 10% probability.
No, but if each point goes with 10% probability, you still might have multiple instances of the same point. Unless I don't know.
Well, I mean, basically, I'm saying, did sampling without replacement, did you look at that as a...
I believe, yeah, you also tried that. I don't think it makes a significant difference. I mean, just actually sampling without replacement makes the sampling a little bit more complicated because you need to track which point you already sampled and exclude them. But otherwise, I don't think it at least in the examples that we showed, since you have enough points, right? Either if you sample with replacement or without replacement, you would have enough to see the important things.
Cool. Heather, your question.
Yes, thanks so much, Omer, for your talk. I really enjoyed it. I had the first question I had actually was John's first question, but then the other one I had was about applications and what you could envision would be good applications. We have quite a bit of, one thing is for biomedical data, if it's too much, it's too large, is that maybe computationally out of reach? Or this, I mean, in some way, what you're proposing might make it more tractable, but
I mean, yeah, in terms of computational costs, it's not much more expensive than computing persistent homology. I mean, you just have to compute a few more persistent diagrams, and maybe if you have, if you take point clouds and take the union, so you have a larger sample, but still it's within the same order, so it doesn't scale much worse than the things that you do in general. Again, the main focus, I mean, we started by just thinking about this bootstrapping and sort of found our way around to this cycle registration and not the other way. So that was our main motivation, but the main thing we tried to explore, but sort of, yeah, where it could be used in more applications, that's sort of things that we're hoping to find in the future, mainly since applications are not our expertise, through collaborations. I imagine that in places where you have, well, especially in places where you try to say you have this big point cloud and you try to just maybe find a few features that you will consider outstanding without having to look at the persistent diagram, or maybe you don't trust the persistent diagrams. These are cases where I think this registration method can be very useful.
Great, well, thanks very much.
Jessie.
Yeah, I'm Gesine Reinhardt. I'm in the statistics department in Oxford. So you can probably guess from which direction my question will go. So when you do the bootstrap, so you often want to estimate the variance as well. So the variability of your estimator. So when you do you have your point estimate, but in order to judge whether something is significant, you also want to estimate the variance or the standard deviation of this estimator. Which I wondered whether you do implicitly with your reweighted score. So I wonder the score which takes the overlap into account. So intuitively, the overlap should somehow appear when you calculate the variance. So if you take different samples, they will have some overlap well, if the sample size is large enough, they will have some overlap in points. And so there might be some corresponding overlap in the barcode length.
Mm-hmm.
And so maybe this is what you do intuitively.
The answer to the question is, looking for it. Yeah, I changed it. I was being careful about calling it bootstrap because it doesn't follow exactly the pipeline of what you're doing. Statistical bootstrap, and I tried to, and I was careful here to put the quotes here. The idea, what will be the equivalent of the estimator here is that you take a data set, and gamma 1 is an estimate. So gamma 1 tells you, okay, there is a cycle here. This is the value that we found. Now I want to tell you how reliable gamma 1 is. So P gamma, in a way, is, instead of having an estimator and variance, we have gamma 1 and P of gamma 1. So gamma 1 is the estimate, and P gamma 1 is the variability or the reliability of this estimate. And that sort of replaces the variance in a way. Probably there are other ways to think about it. And again, it's not exactly the pipeline of what you do in Bootstrap, but it's the same kind of concept that we call it bootstrap-like, or try to be careful about the notion, but that would be the way I would think about it. So your estimates are the cycles that you find, and then instead of taking variance or confidence interval, this is the measure of the reliability of your estimates, which you are bootstrapping from the data.
Yeah, thank you. So, so I can see that reasoning why we want to have P gamma, but I think it could be interesting actually to look at the variability of P gamma and see whether something comes out which is related to the scaling, which you found empirically works better.
Yeah, definitely. I mean, you can make it in another level. You can say, okay, now I have P gamma, which is an estimate of something, and maybe I want to say how reliable this thing is, and that will help you, for example, be able to say, look at these things and tell me which one is really statistically significant and which isn't, right? After computing this scores. Yeah, that's a higher level of the next level of what you can do with that. Yeah.
It might even give you some guidance about the sample size, because if the sample size is too large, you just recover the same thing all the time with a little bit of noise, because you have the Gaussian noise. But if it's too small, you don't recover anything.
Yeah, thank you.
But I think it's really a cool idea.
Thank you.
Wonderful. Thank you very much, Omer, for that talk.